Now, let us discuss the relation between the change of the magnetic flux to the induced electric field, or how the magnetic field induce the magnetic field induce the electric field. Okay. Let's see. Let's discuss this from a simple example. Like here we have a while loop here as a circular loop. This is not necessarily circular, but for simplicity, we can say that okay, we have a while loop here, and we place this while loop in the region with a magnetic field that change in time. Let's assume that in this moment the electric field is increased, meaning the magnitude of the electric field increased, and the magnetic field point into the plane like this. Okay, and we know from the Faraday laws that this will induce the magnetic field by induce the current inside the loop, and this current will induce a magnetic field that against the change of the flux. So the induced magnetic field will point outward from the plane like this, which means that if we use the right-hand loop, we must have that the change of the external magnetic field induce the current in the counterclockwise direction like this. So we can interpret this like the change of the magnetic field produce the electromotive force which acts as a voltage source. Like if we connect a voltage source in this loop, and if we connect the voltage source like this, it will produce a current in this loop. Okay. Again, as we have discussed before, that the current is the moving charge, right? And we define the current from the positive charge. So we can say that when there is a current move in this loop like this, it means that we must have the motion of the positive charge in this Y. And what causes the motion of the positive charge? Of course, the cause of the motion is the electric field. So we can say that the change of the flux or the change of the external magnetic field induce the electric field that point in the direction counterclockwise like this, and this electric field move the positive charge and create the current in this Y. Okay. Now, if we have the electric field and we have the charge, so we must have the electric force Fe equal to QE like this, and this electric force drives the charge through the Y, which means that this force create the work or do the work on the charge. The work done by the electric field can be calculated using its definition, that work is equal to integral of F dot ds, where ds is a displacement vector point in the direction of the motion of the particle. In this case, we can see that the positive charge moves in this direction, so ds point in the counterclockwise direction like this. Okay, and the electric field drives the charge in this direction, so we know that the electric field will point in this direction also. We want to calculate the work done by the electric field, so this is equal to F dot the integral of F dot ds, and F is equal to QE, so we substitute F is equal to QE here, and integral over the loop, okay, over the closed loop, so we have the circle here. This means that the integral over the closed loop. So we have the work done by the electric force is equal to the integral of QE dot ds, which is equal to the change of the electric potential energy from the starting point to the end point. In the case of closed loop, the starting point and the end point are at the same point. So it means that if we start from this point, so this is the starting point, and then the charge move along this path and then come back to the same point. This is the end. Right? The potential energy, electric potential energy change equal to the amount of work done by the electric field. This energy dissipates to the resistance of the wire. Okay? So this complete the circuit. Right? We have the, if we look this at a circuit, it means that we have the source here. The source provides the energy to the charge, and the charge move in the circuit, and the charge loss its energy to the resistance of the circuit. Then it come back to the source to gain the energy again, and then move into the circuit again and again. Now, if we want to write this in terms of the electromotive force or the voltage difference, by definition, the voltage difference is equal to the change of the potential per unit charge. So, if the charge that we think is moved in the circuit is Q, so the voltage difference is delta U over Q, and delta U is this change of the potential energy. This is delta U. Okay, so we have that this is delta U over Q, and it means that if we divide this by Q, so we have this integral of E dot ds, and this delta V is the EMF, right? This is the electromotive force, the force that drives the charge through the circuit. Okay, so we have that the integral of E dot ds is equal to the EMF, and from the Faraday laws, we know that the EMF is equal to the minus of dV by dt. Okay, so it means that we can relate the electric field and the change of the magnetic field or change of the magnetic flux like this. The physical meaning of this equation is that if you change the magnetic flux by changing the magnetic field or by changing the size of the boundary of the loop, okay, you induce the electric field, and the integral of the electric field allow the loop must equal to the minus of the change of the dVb by dt. The minus sign again can be interpreted using the Lenz's law, that the current that induced or the current that drives by the electric field will be in the direction that produce the induced magnetic field that against the change of the magnetic flux. So now we have that the magnetic flux can induce the magnetic field. That is what we discussed at the first of this lecture, that we now have the law or the expression that shows us that the change of the magnetic field is will induce the electric field. Okay, in the previous lecture we know that the electric field can induce the magnetic field. Now we know that the magnetic field can also induce the electric field.